ਹੈਲੋ ਸਟੂਡੈਂਟਸ, ਗ੍ਰੈਵਿਟੇਸ਼ਨ ਦੇ ਇਸ ਟੌਪਿਕ ਵਿੱਚ ਤੁਹਾਡਾ ਸਵਾਗਤ ਹੈ। ਅਰਥ ਤੇ ਗ੍ਰੈਵਿਟੀ ਨੂੰ ਓਵਰਕਮ ਕਰਕੇ ਆਸਮਾਨਾਂ ਵਿੱਚ ਉੜਨਾ ਮਨੁੱਖ ਦੀ ਬੜੀ ਪੁਰਾਣੀ ਖੁਆਇਸ਼ ਹੈ। ਰਾਮਾਇਣ ਦੇ ਪੁਸ਼ਪਕ ਵਿਮਾਨ ਤੋਂ ਲੈ ਕੇ ਲਿਓਨਾਰਡੋ ਦਾ ਵਿੰਸੀ ਦੀ ਫਲਾਈਂਗ ਮਸ਼ੀਨ, ਮੌਂਟਗੋਲਫਾਇਰ ਬ੍ਰਦਰਜ਼ ਦੇ ਹੌਟ ਏਅਰ ਬੈਲੂਨਸ ਅਤੇ ਰਾਈਟ ਬ੍ਰਦਰਜ਼ ਦਾ ਸਭ ਤੋਂ ਪਹਿਲਾ 에ਅਰਪਲੇਨ ਇਸ ਦੇ ਸੂਚਕ ਹਨ। ਅੱਜ ਅਸੀਂ ਪੜ੍ਹਾਂਗੇ ਕਿ ਅਰਥ ਦੀ ਗ੍ਰੈਵਿਟੀ ਓਵਰਕਮ ਕਿਵੇਂ ਕੀਤੀ ਜਾ ਸਕਦੀ ਹੈ। First of all, I'd like to share the learning objectives of today.
On completion of this topic, learners will be able to describe gravitational field strength, describe the gravitational potential and discuss gravitational potential energy, discuss the importance of escape velocity.
Let us study gravitational interaction in terms of gravitational field. Gravitational field ਉਹ ਖੇਤਰ ਹੈ ਜਿੱਥੇ gravitational force ਮਹਿਸੂਸ ਕੀਤਾ ਜਾ ਸਕਦਾ ਹੈ। ਤੁਸੀਂ ਜਾਣਦੇ ਹੋ ਕਿ gravitational force ਅਤੇ electromagnetic force distance ਤੋਂ ਕੰਮ ਕਰਦੀਆਂ ਹਨ। ਕਿਉਂਕਿ ਬੋਡੀਜ਼ ਕੰਟੈਕਟ ਵਿੱਚ ਨਹੀਂ ਹੁੰਦੀਆਂ, ਇਸ ਕਰਕੇ ਇਹ ਮੰਨਿਆ ਜਾਂਦਾ ਹੈ ਕਿ ਇਹ ਆਪਣੇ ਰੀਜਨ ਆਫ ਇਨਫਲੂਐਂਸ ਵਿੱਚ ਆਏ ਆਬਜੈਕਟਸ ਉੱਤੇ ਇੱਕ ਫੋਰਸ ਫੀਲਡ ਕਰਕੇ ਐਕਟ ਕਰਦੀਆਂ ਹਨ। ਗ੍ਰੈਵਿਟੇਸ਼ਨਲ ਫੋਰਸ ਵਾਂਗ ਇਲੈਕਟ੍ਰੋਮੈਗਨੈਟਿਕ ਇੰਟਰੈਕਸ਼ਨ ਵੀ ਇਨਵਰਸ ਸਕੁਆਇਰ ਲਾਅ ਫੋਲੋ ਕਰਦੀ ਹੈ। ਇਲੈਕਟ੍ਰੋਮੈਗਨੈਟਿਕ ਇੰਟਰੈਕਸ਼ਨ ਨੂੰ ਤਾਂ ਫੀਲਡ ਕਨਸੈਪਟ ਦੀ ਟਰਮਸ ਵਿੱਚ ਕੰਪਲੀਟਲੀ ਡਿਸਕ੍ਰਾਈਬ ਕੀਤਾ ਜਾ ਸਕਦਾ ਹੈ, ਪਰ ਗ੍ਰੈਵਿਟੇਸ਼ਨਲ ਫੋਰਸ ਫੀਲਡ ਇਸੇ ਤਰੀਕੇ ਨਾਲ ਡਿਸਕ੍ਰਾਈਬ ਨਹੀਂ ਹੋ ਸਕਦੀ। We know a body experiences gravitational force in the presence of another mass. A mass creates a gravitational field around itself when another mass enters the region of influence. It experiences gravitational force which is given by Newton's law of gravitation. Gravitational field strength E is equal to gravitational force experienced by unit mass in a gravitational field. Mathematically, it is equal to force per unit mass. Its unit is Newton per kilogram. It is a vector quantity and obeys the rules of vector algebra, including superposition principle. For a number of bodies, the net gravitational field due to them at a given point is vector sum of all the individual fields. Let us see the physical significance of gravitational field strength.
Let m be the mass of a spherical object. We have to find the field strength due to this mass at point P at a distance r from the center O of the object. Let us place a test mass m at the observation point P. According to Newton's law of gravitation, the force on the test mass small m at the point P is given by F equal to g times the product of the mass of the object capital M and test mass small m upon the square of the distance small r between them. Since E is equal to F upon m, therefore the gravitational field strength of the object at the point P is E equal to g into capital M upon r square. The direction of the gravitational field at the point P is along PO. That is, gravitational field is directed towards the center of the object. It is clear that the gravitational field decreases as the distance r increases and becomes zero at infinity. The direction of the gravitational field is always towards the center of the object.
The expression of gravitational field reveals that it is exactly same as that of the acceleration of a body of mass m acted upon by an external force F. Clearly, acceleration A is the same as E. That is why dimensionally gravitational field strength is same as acceleration. If we have Earth in place of the spherical object, the gravitational field strength of the Earth at the point P is E Earth equal to G into me upon r square. If you compare the Earth's gravitational field strength and acceleration due to gravity at a distance r, you will find that the Earth's gravitational field strength is equal to the gravitational acceleration g dash. However, gravitational field strength at a point on the surface of Earth can be obtained by setting r equal to Re. Therefore, the gravitational field strength at a point on the surface of Earth is given by E Earth equal to G into me upon Re square, also equal to gravitational acceleration g. Field strength ਕਿਸੇ ਰੀਜਨ ਨੂੰ ਮੈਪ ਕਰਨ ਅਤੇ ਫੀਲਡ ਵਿੱਚ ਬੋਡੀ ਉੱਤੇ ਕੰਮ ਕਰ ਰਹੀ ਫੋਰਸ ਕੈਲਕੂਲੇਟ ਕਰਨ ਲਈ ਇੱਕ ਕਨਵੀਨੀਐਂਟ ਟੂਲ ਹੈ। ਜਿਵੇਂ ਜੇ ਗ੍ਰੈਵਿਟੇਸ਼ਨਲ ਫੀਲਡ ਸਟਰੈਂਥ ਪਤਾ ਲੱਗ ਜਾਵੇ ਤਾਂ ਅਸੀਂ ਗ੍ਰੈਵਿਟੇਸ਼ਨਲ ਫੀਲਡ ਲਈ ਰਿਸਪੌਂਸਿਬਲ ਬੋਡੀਜ਼ ਨਾਲ ਕੋਈ ਖਾਸ ਕੰਸਰਨ ਨਹੀਂ ਰੱਖਦੇ। ਗ੍ਰੈਵਿਟੇਸ਼ਨਲ ਫੀਲਡ ਵਿੱਚ ਐਂਟਰ ਕੀਤੇ ਕਿਸੇ ਮਾਸ ਤੇ ਐਕਟਿੰਗ ਗ੍ਰੈਵਿਟੇਸ਼ਨਲ ਫੋਰਸ ਇਸ ਮਾਸ ਨੂੰ field strength ਨਾਲ multiply ਕਰਕੇ compute ਕੀਤੀ ਜਾਂਦੀ ਹੈ। Let us have a look at some advantages of gravitational field. ਅਸੀਂ gravitational field ਲਈ responsible body ਦਾ mass ਜਾਣੇ ਬਗੈਰ ਵੀ ਉਸ ਤੇ acting gravitational force measure ਕਰ ਸਕਦੇ ਹਾਂ। The concept of field strength allows us to study gravitational field in terms of the mass of one body. ਫਿਰ ਇਹ ਗ੍ਰੈਵਿਟੇਸ਼ਨਲ ਫੋਰਸ ਦੀ ਮੈਥਮੈਟੀਕਲ ਕੈਲਕੂਲੇਸ਼ਨ ਨੂੰ ਸਿੰਪਲੀਫਾਈ ਕਰਦੀ ਹੈ। ਜ਼ਰਾ ਸੋਚੋ, ਜੇ ਗ੍ਰੈਵਿਟੇਸ਼ਨਲ ਫੋਰਸ ਕੈਲਕੂਲੇਟ ਕਰਨ ਲਈ ਹਰ ਵਾਰੀ ਬੋਡੀ ਦਾ ਮਾਸ ਅਤੇ ਅਰਥ ਦਾ ਮਾਸ ਮਲਟੀਪਲਾਈ ਕਰਕੇ ਉਹਨਾਂ ਵਿਚਕਾਰ ਡਿਸਟੈਂਸ ਦੇ ਸਕੁਆਇਰ ਨਾਲ ਡਿਵਾਈਡ ਕਰਨਾ ਪਵੇ ਤਾਂ ਕਿੰਨਾ ਮੁਸ਼ਕਿਲ ਹੋਵੇਗਾ। We know that the concept of potential energy is linked to a system, not to a single particle or body. Potential energy is the energy stored in the body at its given position. If the position of the body changes on account of forces acting on it, then the change in its potential energy is just the amount of work done on the body by the force. For example, when a weight is lifted up, the force of gravity will try to bring it back down to its original position. The initial steps of lifting the weight require energy to perform. Since energy cannot be created or destroyed, this energy cannot disappear, but is stored as potential energy. Generally, potential energy of a system is the energy of position. That is, the energy a system is considered to be due to the positions of its components in space. There are a number of different types of potential energy, each associated with a particular type of force. Potential energy of a body arising out of gravitational force is called gravitational potential energy. Similar to potential energy, gravitational potential energy is linked to a system. Gravitational energy is not limited to Earth, but is applicable to any two masses of any size and at any location. Let us now calculate the gravitational potential energy of a body of mass m situated close to the surface of Earth, that is at an altitude which is much smaller than the radius of the Earth. In such cases, the force of gravity is practically a constant equal to mg directed towards the center of the Earth. If we consider a point at a height h1 from the surface of the Earth and another point vertically above it at a height h2 from the surface, the work done in lifting the particle of mass m from the first to the second position is denoted by W, which is equal to force into displacement or mg into h2 minus h1. If we associate potential energy U at a point at height h above the surface such that U equal to mgh plus u0, where u0 is constant. However, u0 is the potential energy on the surface of the Earth, because at h equal to 0, u is equal to u0. It is clear that work done W is equal to u2 minus u1. Here the constant u0 cancels out. So, the work done in moving the particle is just the difference of potential energy between its final and initial positions. If we consider points at arbitrary distance from the surface of the Earth, the result we have just derived is not valid, since the assumption that the gravitational force mg is a constant is no longer valid. Let us now calculate the gravitational potential energy of a body of mass m situated at a distance r from the center of the Earth. The gravitational potential energy of a body at a point is defined as the amount of work done in bringing the body from infinity to that point against the gravitational force. When the body is at infinity, its gravitational potential energy is 0. It is called zero level of potential energy. Consider that the Earth is a uniform sphere of radius re and mass me. We have to determine the gravitational potential energy of the body of mass m lying at a point A such that OA is equal to small r. Let the gravitational potential energy of the body at point A be U, which is equal to the work done in bringing the body from infinity to the point A. Suppose that at any instant the body is at the point P, such that OP is equal to x. Then the gravitational force on the body at the point P is given as force equal to g times the product of the me and m upon x square. Let dW be a small amount of work done in moving the body through infinitesimally small distance pq, which is equal to dx and is given as dW equal to f dx. Hence, dW is equal to g into the product of the me and m upon x square into dx. Therefore, work done in bringing the body from infinity to the point A would be the integration of g into me into small m upon x square into dx with limits infinity to r, that is W equal to g into me into small m into the integration of 1 upon x square into dx with limits infinity to r. This gives W equal to minus capital G into me into small m into 1 upon x with limits infinity to r. Therefore, work done W is equal to minus capital G into me into small m upon r. This work done is stored inside the body as its gravitational potential energy. Therefore, the gravitational potential energy capital U of a body of mass small m at distance small r from the center of the earth is given by minus capital G into me into small m upon r. Therefore, gravitational potential energy of a body at a height h above the surface of the earth is minus capital G into me into small m upon re plus h. Here, negative sign shows that potential energy of the body is due to the attractive force by the earth on the body. This means to bring the body from infinity to a distance small r. Work is done by the gravitational field of the earth. Difference in potential energy has an importance. Let us see how. If a body of mass small m is moved from a point at distance small r1 to a point at distance r2, then change in potential energy of the body is given as delta U, which is equal to integration of G into me into small m upon x square into dx with limits r1 to r2. That is equal to G into me into small m into the integration of 1 upon x square dx with limits r1 to r2. On solving, we get delta U equal to minus G into me into small m into 1 upon x with limits r1 to r2. Therefore, delta U is equal to G into me into small m into 1 upon r1 minus 1 upon r2. J r1 r2 ਤੋਂ greater ਹੋਵੇ ਤਾਂ body ਦੀ potential energy ਵਿੱਚ negative change ਹੋਵੇਗਾ। यानी ਜੇ body earth ਤੋਂ ਨੇੜੇ ਲਿਆਂਦੀ ਜਾਵੇ ਤਾਂ ਇਸ ਦੀ potential energy ਘਟ ਜਾਵੇਗੀ। In case the body is moved from the surface of earth to a point at distance h above the surface of earth, then the change in potential energy will be delta U equal to capital G into me into small m into 1 upon re minus 1 upon re plus h. This is equal to G into me into small m upon re into 1 minus re upon re plus h, or G into me into small m upon re into 1 minus 1 plus h upon re raised to the power minus 1. Using binomial expansion, we get delta U is equal to G into me into small m upon re into 1 minus h upon re plus terms with higher powers of h upon re. In case h is very small as compared to the radius of the earth, the factors containing higher powers of h upon re can be neglected. Then delta U becomes equal to G into me into small m into h upon re square. On substituting the values of small g at the earth's surface, this expression for change in gravitational potential energy becomes equal to mgh. However, this expression holds only when the value of small g does not change over the distance h. This is the same expression that we have obtained for potential energy of a body of mass small m at a height h above the surface of earth. It is clear that near the earth's surface, mgh and capital G me small m upon r are in close agreement. However, for larger r, gravitational potential energy does not continue rising as rapidly as it would near the Earth's surface. We have calculated the potential energy at point of a particle due to gravitational forces acting on it due to Earth, and it is proportional to the mass of the particle, whereas the gravitational potential due to the gravitational force of the Earth is defined as the potential energy of a particle of unit mass at that point. We know that the gravitational potential energy of a body at a point is defined as the amount of work done in bringing the body from infinity to that point against the gravitational force. Therefore, gravitational potential at a point in the gravitational field of the Earth is defined as the amount of work done in bringing a body of unit mass from infinity to that point. We know that the gravitational potential energy associated with two particles of masses m and m0 separated by distance small r is given as u equal to minus g into m0 upon r. Obviously, gravitational potential at a distance r from the center of the body of mass small m can be obtained by setting m0 equal to 1. Therefore, gravitational potential due to a mass m at a distance small r is given as v equal to minus g into m upon r. Similarly, gravitational potential energy capital U of a body of mass small m at distance small r from the center of the Earth is given by minus g into me into small m upon small r. And gravitational potential at a distance small r from the center of the Earth can be obtained by setting m equal to 1. Therefore, gravitational potential due to the Earth at a distance small r from its center is given as v equal to minus g into me upon small r. This shows that the gravitational potential at a point is always negative, increases on moving towards infinity and becomes 0 at infinity. At the surface of the Earth, the gravitational potential is given as V0, which is equal to minus g into me upon re. The unit of gravitational potential is joule per kilogram. Can you tell me the unit of gravitational potential energy? The unit of gravitational potential energy is joule. In a novel named From the Earth to the Moon, written in 1865, the author imagined launching a spacecraft to the moon by firing it straight upward from cannon. Today, rockets fired into space operate according to the same basic idea.
ਜੇ ਇੱਕ ਸਟੋਨ ਉੱਪਰ ਵੱਲ ਸੁੱਟਿਆ ਜਾਵੇ ਤਾਂ ਇਹ ਇੱਕ ਸਰਟਨ ਹਾਈਟ ਤੱਕ ਜਾ ਕੇ ਮੁੜ ਅਰਥ ਦੇ ਸਰਫੇਸ ਤੇ ਆ ਜਾਂਦਾ ਹੈ। ਮਸ਼ੀਨਾਂ ਦੀ ਹੈਲਪ ਨਾਲ ਇਸ ਆਬਜੈਕਟ ਨੂੰ ਹੋਰ ਉੱਪਰ ਅਤੇ ਕਿਤੇ ਗ੍ਰੇਟਰ ਸਪੀਡਸ ਨਾਲ ਮੂਵ ਕਰਾਇਆ ਜਾ ਸਕਦਾ ਹੈ। ਇਸ ਨੂੰ ਜ਼ਿਆਦਾ ਤੋਂ ਜ਼ਿਆਦਾ ਇਨੀਸ਼ੀਅਲ ਸਪੀਡ ਦੇ ਕੇ ਉੱਚੀਆਂ ਤੋਂ ਉੱਚੀਆਂ ਹਾਈਟਸ ਤੇ ਪਹੁੰਚਾਇਆ ਜਾ ਸਕਦਾ ਹੈ। ਇਸ ਦਾ ਅਰਥ ਹੋਇਆ ਕਿ ਸਟੋਨ ਦੀ ਹਾਈਟ ਅਚੀਵਡ ਕਰਨੀ ਇਸ ਦੀ ਵੈਲੋਸਿਟੀ ਆਫ ਪ੍ਰੋਜੈਕਸ਼ਨ ਤੇ ਡਿਪੈਂਡ ਕਰਦੀ ਹੈ। ਹੁਣ ਜੇ ਸਟੋਨ ਨੂੰ ਸਫੀਸ਼ੈਂਟਲੀ ਲਾਰਜ ਵੈਲੋਸਿਟੀ ਦਿੱਤੀ ਜਾਵੇ ਤਾਂ ਇਹ ਗ੍ਰੈਵਿਟੇਸ਼ਨਲ ਪੁੱਲ ਅਤੇ ਅਰਥ ਦੇ ਐਟਮੋਸਫੇਅਰ ਦੀ ਰੈਜ਼ਿਸਟੈਂਸ ਨੂੰ ਓਵਰਕਮ ਕਰਕੇ ਐਟਮੋਸਫੇਅਰ ਵਿੱਚ ਕਦੀ ਵੀ ਵਾਪਸ ਨਾ ਆਉਣ ਲਈ ਬਾਹਰ ਨਿਕਲ ਸਕਦਾ ਹੈ।
This minimum velocity with which a body must be projected up so as to enable it to just overcome the gravitational pull is known as escape velocity. Consider that the Earth is a sphere of mass m and radius re. We further suppose that a body of mass small m is at the point P at a distance small x from the center of the Earth. Then the force F exerted by the Earth on the body is given by capital F, which is equal to g into me into small m upon x square. Therefore, work done in moving the body against gravitational attraction through an infinitesimally small distance dx is given by dw, which is equal to f into dx or g into me into m upon x square into dx. Total work done to move the body from the surface of the Earth to a point at infinity, where the gravitational pull would reduce to 0, can be obtained by integrating both the sides of this relation within the proper limits, that is, x equal to re to infinity. On solving, we get w equal to minus g into me into small m into 1 upon x with limits re to infinity. Therefore, work done w is equal to g into me into small m upon re. This work required to project the body so as to escape the gravitational pull is performed on the body by providing an equal amount of kinetic energy to it at the surface of the Earth. The kinetic energy will be just enough to provide it the necessary escape velocity. If Ve is the required escape velocity, then kinetic energy which should be given to the body on the surface of Earth is half m Ve square. Since this amount of kinetic energy is equal to the amount of work required to project the body to escape the gravitational pull. Therefore, half m Ve square is equal to g into me into small m upon re. This gives Ve equal to the square root of twice g me upon re. The value of acceleration due to gravity at the surface of Earth is small g equal to g me upon square of re. Therefore, on substituting the value for ge into me, we get Ve equal to under root of twice small g re. This is the relation for the escape velocity. It is clear that it does not depend upon the mass of the body to be projected. This relation for escape velocity applies equally well to an object thrown from the surface of the moon or from the surface of any other celestial body. Escape velocity on the surface of Earth is 11.2 kilometer per second. I hope you are well versed with the concept of gravitation. Let us now summarize today's topic. Gravitational field strength of the Earth at a distance small r from its center is E Earth equal to g into me upon small r square. Gravitational potential energy of a body at a point is defined as the amount of work done in bringing the body from infinity to that point against the gravitational force, whereas gravitational potential due to the gravitational force of the Earth is defined as the potential energy of a particle of unit mass at that point. Escape velocity is the velocity with which a body must be projected up so that it can just overcome the gravitational pull. So now we come to the end of today's topic. Here is a quick question answer session for you to find out how much have you actually absorbed. The first question is, give the relation for gravitational potential at the surface of the earth. The answer to this is, at the surface of the earth, the gravitational potential is V0 equal to minus g into me upon re. The next question is, give the expression for escape velocity at the surface of the earth. The answer, at the surface of the earth, escape velocity Ve is equal to the square root of twice g re. मैं हुण इस आस नाल टॉपिक का अंत करदी हाँ कि अज पढ़ाया गया ये टॉपिक तुहाडे लई लाभदायक रहेगा। टॉपिक ते ध्यान देण लई सारिਆਂ ਦਾ ਧੰਨਵਾਦ। अगली क्लास तक ऑल द बेस्ट।